Welcome everybody for this session. Our speaker is Tian from Academy of Mathematics and System Science in Beijing, China. And the title of his talk is The Arithmetic of Quadratic Twists of Elliptic Curves. And as mentioned, it's in memory of John Henry Coates, who we all knew well. Tian, the floor is yours. The screen is yours.
Thanks for the introduction. I would like to also thank the ICM committee for the opportunity to give this talk. I wish to dedicate this talk to the inspiring memory of John Coates. So let me start with the congruent number problem. Recall that a positive integer is called a congruent number if it is the area of a right triangle with rational side lengths. For example, 5, 6, and 7 are congruent number. This is known by Fibonacci. And 1, 2, 3 are non-congruent numbers. This was proved by Fermat. There's one more example. The number 2022 is congruent with the simplest right triangle having side lengths like this. So the so-called congruent number problem is to determine whether or not a given positive integer is a congruent number. So the first theoretical result on congruent numbers is given by Heegner in 1952. He proved that any prime or twice of prime congruent to 5, 6, 7 mod 8 is a congruent number. So in 2012, I proved the following result. For any positive integer k, there are infinitely many congruent numbers among all square-free integers congruent to 5 mod 8 with the exact k odd prime factors. The same result holds also for residual class 6 mod 8 or 7 mod 8. And further, we have the following result. At least half of square-free positive integers congruent to 5, 6, or 7 mod 8 are congruent numbers. A remark. So our generalization of Heegner's result by introduce an induction argument. So the induction is on the number k of prime factors of the number, which involves their functions and the Gauss-Zagier and Watts-Perget formula. So we actually construct explicitly congruent numbers to which contains the congruent numbers constructed by Heegner. Now let's come to this general phenomenon about the quadratic twist of elliptic curves over Q. So congruent number problem is essentially about the quadratic twist family ny squared equals x cubed minus x. So in general, for a elliptic curve over Q, say given by Weierstrass equation y squared equals x cubed plus ax plus b. So let A denote the set of all isomorphism classes of its quadratic twists. So as elliptic curves in this script A varies, we are interested in the behavior of this arithmetic invariance like rank of model V group, order of Schaffer-Tate group, even its P part, or the FP dimension of P Selmer group, or ZP co-rank of the P infinity Selmer group. And also like analytic invariance, like a leading term of the error function in the Taylor expansion around its center, like the order of the error function at the center, or the leading coefficient of the Taylor expansion. We call it the analytic SHA. So in this talk, we focus on the error function side, although some of the discussions are related to Selmer groups. The conjectures, there are two conjectures on leading term about error function under quadratic twist. The first one is given by Goldfeld, which is about the vanishing order of error series. So let A be a quadratic twist family of elliptic curves over Q. So among all elliptic curves A in the family with root number positive 1, then the vanishing order of the error series equal to 0 has density 1. So we call this case, this part of Goldfeld's conjecture, even parity Goldfeld conjecture. So if net A varies in the family with root number -1, then the density of elliptic curves with vanishing order 1 is 1. So we call this odd parity Goldfeld conjecture. The behavior of analytic Shah, namely the leading coefficients of the error series, is very subtle. However, Kolyvagin proposed the following conjecture. So for any quadratic twist family A and P any prime, there is a elliptic curve in the family such that the central value is non-vanishing and P does not divide the analytic Shah of A. Also, there exists elliptic curve in this family with vanishing order 1, and the analytic Shah is not divisible by P. Actually, Kolyvagin proposed his conjecture for modularity rank and the Shah-Faraday group. But if you assume BST conjecture, then so his conjecture implies this analogous. Now let's come to Goldfeld conjecture for same elliptic curves. One of our main results is the following. So for quadratic twist families of same elliptic curves over Q, we have the following. First, the even parity Goldfeld conjecture holds if the same field is not Q join squared -2. And the second one, the other parity Goldfeld conjecture holds if 2 splits in the same field. So there is only one quadratic family with such a property, namely the family containing the curve of conductor 40 line. Yeah, but we just stated in this way. So combine 1 and 2, we have the full Goldfeld conjecture holds for the family, quadratic twist family containing the curve of conductor 40 line. So the proof of the result consists of 2 parts. The first one is our journal work with Branger and Branger-Costa-Skinner. So let A be a semi-elliptic curve over Q, P a prime, and R being 0 or 1. Then the rank R P converse holds. So the rank R P converse means the implication from elliptic co-rank of P infinite Selmer group of A being R to the vanishing order of error series being R. Here we require extra condition. If for R equals 1, we need P being ordinary. And the second part of the, the proof is obviously follows from these 2 theorems. And the other one is the celebrated result of Alex Smith. So he proved the 2 infinity Selmer analogous of Goldfeld conjecture holds for family A over Q, satisfying following assumptions. I will introduce his assumption later. But here, the two infinite Selmer analogous means we state the Goldfeld conjecture replaced with this co-rank. Z2's co-rank of two infinite Selmer group, but replace this order of vanishing of L function by co-rank of two infinite Selmer group. So we call that version or two infinite Selmer analogous of Goldfeld conjecture. So the mild assumption in Smith's result is the following. So he assumed there is a elliptic curve in the quadratic family such that one of the following holds. So if the elliptic curve has no non-trivial two-torsion rational points, or if the rational points killed by 2 is of this one-dimensional over F2, and for the unique co-degree 2 isogeny A to A0, the field generated over Q by these two torsion points of A0 is not Q, and also not the Q join the two torsion points of A. Or this A has full rational two torsion points, and A has no cyclic degree 4 isogeny over Q. Actually, in many cases, Smith proved the Selmer analogous Goldfeld conjecture while establishing the following result. The distribution of two infinite Selmer groups in the family follows the same principle in the BKL-PR conjecture for p equals 2. Now let's recall this conjecture given by Bagawa, Kanan, Nenstra, Poonen, Rain. So this conjecture is not for elliptic curve over a quadratic family, but for quadratic field, for elliptic curves, all quadratic field elliptic curves over a fixed number field F, or even the global field F. So the conjecture says let script AF be the set of all isomorphism classes of elliptic curves over a fixed global field F, ordered by height, for R equals 0 or 1, and for any finite symplectic P group, the same P infinite Selmer group isomorphic to R copies of copy over ZP direct sum with G has density. So we require the root number of A being -2 to the R, and then the density of such elliptic curve is given by the right-hand side. So in particular, the average of order of two Selmer group of A over F is exactly 3. And also this conjecture implies the density of elliptic curves with rank 0 among all elliptic curves over F with root number plus 1 is 1. And also density of elliptic curves with rank 1 among all elliptic curves with root number -1 is also 1. Okay, so even though this conjecture is for all isomorphic classes of elliptic curves over a fixed number, not just for quadratic twist family, but it turns out it's very useful for the result we mentioned before. Okay, so to discuss the general situation, we need to introduce the equivalent relation for quadratic twist family. For this general case, the distribution of Selmer groups does not follow the the BKL-PR's principle, even though the case handled by many cases handled by Alex Smith follows, but in general, it does not. So for any quadratic twist family A, let sigma be a finite set of places of Q containing to infinity and all primes P, where any member in the family has better reduction at P. So we define two elliptic curves in the family are called sigma equivalent if they are isomorphic over QV for all V in sigma. One can show the root numbers of elliptic curves in a fixed class X with respect to this relation, equivalent relation, are the same. So we denote this root number by epsilon X. In this talk, we focus on elliptic curves with 4 rational 2 torsion points. So for such families, there are 3 kinds of 3 types. The first type, the elliptic curves in the family does not have a rational cyclic for isogeny. For example, the congruent number elliptic curve family, the ny squared equals x cubed minus x. So it does not have a rational cyclic for isogeny. So this case was discussed by Smith's work. But there are another 2 types. So first, type B, A has a rational cyclic for isogeny, and for any A in the family, these 4 torsion points of A not all defined over Q join squared negative 1. For example, this ny squared equals x times x minus q 3 times x plus 1. This is called so-called tiny number elliptic curve family. And the last type C, A has a rational cyclic for isogeny. And for some member in the quadratic twist family, this elliptic curve A, all its 4 torsion points are defined over Q join I. For example, this ny squared equals x times x minus 9 times x minus 25. Now we discuss the distribution of 2 Selmer group of this A instead of 2 infinity, because this is 2 Selmer group is simpler and some result we have only for 2 Selmer group, and it's already you can already see some new phenomena for type B and C. So distribution of 2 Selmer group for type A. The distribution of 2 infinity Selmer groups is independent of equivalent classes of X. So this is a result of Hesbrown, Savannah-Dyer, and King. So let A be a quadratic twist family of type A, and X are equivalent class. Then for any D, non-negative integer with the right sign, with the right parity. So the probability of the elliptic curves in the class with F2 dimension of 2 Selmer mod 2 torsion points equals to T is given by the right-hand side. So this result about 2 Selmer group distribution of 2 Selmer group is also the starting points of Smith's work on 2 infinite Selmer group of type A. So there is a corollary. The average of order of 2 Selmer group mod 2 torsion points for A runs over this class of type A is always 3. So in this, if you restrict your elliptic curve in any equivalent class, the phenomena, the rules is the same. But for type B and C, this is a result in progress. This joint work with Pan. Let A be a family of type B or C, and X is a equivalent class. Then there is an integer T for type B or a pair of integers for type C. This pair is unordered. Only depend on the equivalent class X with the property. So the parity of T is same as this epsilon X for type B, and the parity of Ti is same as the parity is the same as this epsilon X for I equals 1 and 2, and the sum of T1 plus T2 is non-positive for type C, such that for any non-negative integer with the right parity, and the density of elliptic curves in the equivalence X of with property F2 dimension of two Selmer mod two torsion points equals to D is given by a rational number times this product, the infinite product. So here, if D less than T for type B, or D less than the maximum of T1, T2 for type C, this rational number is just 0. So actually there is no any, not just density is 0, but there is no any curve with this F2 dimension on these two Selmer mod two torsion points. So otherwise, for D bigger or equals to T or maximum of T1, T2, this alpha dt are positive, explicit positive rational number, only depends on D and T, of course. Also this class X. So moreover, if we make this sigma larger, like a sigma prime, then for any sigma prime equivalent classes, X prime containing X has the same T and alpha dt. So the final statement tells us the equivalent classes maybe is a good notion for the distribution of Selmer groups, even or the analytic SHA and so on. We expect to establish the distribution of two infinite Selmer groups for type B and C, starting from this result. So there is a corollary. The average of order of two Selmer mod two torsion points for a running over this equivalent class X is equal to 3 plus 2 to the T's power for type B, and 3 plus 2 to the T1 plus 2 to the T2 for type C. You say, but for type A, or for all elliptic curves over a global field, fixed one. So the average of two Selmer order is 3, but here the situation changed. So now we are in the situation that, so first the Kolyvagin conjecture predicts that for R equals 0 or 1, the dimension of F2 dimension of two Selmer mod two torsion points, when A runs over the whole quadratic twist family with sign plus, then they can reach the minimal 0. And if we replace sign plus by sign minus, then this dimension will reach minimal 1. So this is the Kolyvagin's original conjecture for analytic SHA or analogous for SHA. But we just see from the previous the result. Distribution has nicer behavior when restricted in equivalent classes. But for some classes X, this dimension, F2 dimension, cannot reach the minimal 0 or 1. So it seems natural to consider the following variation of Kolyvagin's problem. So this is the question. For an equivalence classes X of quadratic twists of elliptic curves over Q and a prime P, let R be 0 or 1 with this parity of R equal to epsilon X. So we ask, what's the behavior of the P order of analytic shot of A, the minimal value of that one, when A runs over in the equivalent classes with the analytic order being 0 or being 1. So we extend Kolyvagin's conjecture to such a problem. For example, if I give you two equivalent class X1 and X2, what's the difference of these two minimal value? So I think Prasanna considered this question in his thesis work. So suitable constructed arithmetic or the theta series or arithmetic theta series on SL2 tilde have Fourier coefficients basically exactly the analytic shot of A when A runs over the given class with analytic rank with the right analytic rank 0 or 1. So namely A equals 0 if the epsilon X equals 1 plus 1, or RA equals 1 and the epsilon X is -1. Okay, so this theta series or arithmetic theta series constructed by Yuan Zhang tell you, so if you make this series like explicitly, then you can say precisely the analytic shot on the Fourier coefficients of this series. Okay, now this observation brings this theory of V repetition theta difference into study the problem of Kolyvagin, the extension. Okay, first, let's recall some modularity result of a Heegner cycle. So before that, let's recall some classical theta lifting. Let psi being a fixed non-trivial additive character of A over Q. A is the ideal of Q. B is a quaternion algebra over Q, and V is a trace zero subspace of B. And let H be in PB cross. So this is isomorphic to SO3. And G, the doubling covering of SL2A. Let VA, this SVA is the Schwarz space on VA. It has a V repetition of HA, the other points of H times G. So we denote the V repetition by omega. So for an automorphic repetition pi containing in the of the HA, so the theta kernel defined by this V repetition. So you use this omega GH acts on the Schwarz function phi, and then you make an evaluation over all rational points of the vector space V and sum it. So this is automorphic in G and also in H. So this automorphic kernel defines a lifting from automorphic repetition of HA to automorphic repetition of G. So we denote this lifting being theta pi of pi. Now there is an arithmetic theta lifting. So in arithmetic theta is the case, there is no such a simple construction directly from V representation of theta kernel. Now let's recall this, let's give the situation first. So B is an incurrent definite quaternion algebra over A, and V is the trace zero subspace, submodule. And Schwarz functions on V has the V representation again of this PB cross times this big G. The big G is same as before. So associated to this quaternion algebra in current one, there is a small curve over Q, and let J denotes its Jacobian. So suppose we are given a elliptic curve with sign -1, which is parameterized by the small curve X. Then we can consider all homomorphism from the Jacobian of X to A as abelian varieties, and the tensor with Q, then you get a covector space. This covector space is admissible as the representation of this big H finite part. Now a theorem of YZZ about the modularity of Heegner cycle, we call it arithmetic theta lifting, is the following. So they construct the automorphic, the theta kernel, so which is similar to theta kernel in classical situation, using CM points, such that the theta lifting of pi A, so pi A plays the same role as the automorphic representation of HA in the classical situation. So this lifting just defined simply consists of this theta kernel composed with F. When F runs over this pi A, this admissible representation of big H, and the phi runs over the Schwarz function on V. So this one is a representation of big G, with but this space is endowed with the pairing given by Leontief height and also Tamagawa measures. So now another main result of this talk is this arithmetic Rallis inner product formula. So if we fix decomposition of base change of pi A to C, so this is restrict the tensor product of local ones pi V, and on each pi V we fix HV invariant pairing we call it Bragg V, such that for any pure tensor Fi, so this Fi you may view it as morphism from X to A. But this X is a small curve with different level. So this is the inverse system. So we call this, we denote a member in this inverse system like FIU. So U runs over all open compact subgroup of this H. And then we require the pairing of the local ones, the product, equals essentially the degree of F, or the here is this the dual of F2 composed with F1. So this is actually an integer. So this is ongoing work with Wei He and Wei Xiong. So we prove the following result. For any pure tensor F1, F2 in this automorphic representation pi A, and phi1, phi2 Schwarz functions, the following equality holds with standard measures, Tamagawa measures. So the inner product of these two theta lifting we constructed in this YZ's work. So this theta phi1 F1, theta phi2 F2. So this one, the Leontief height, the inner product of them equals to the derivative of air function at the center divided by zeta 2 times, so this L2 1Q means the complete zeta function, zeta function times some local factor. So this V runs over all places of Q, and this local coefficients is the matrix coefficients of the V repetition, which is on the Schwarz space, times the matrix coefficients of our pi A. So this is like a HF1V coupled with F2V. So this is the product of the two matrix coefficients. You integrate over HV. So this gives us this local factor of in the formula. Okay, so in this formula, on the right hand, on the left hand side, there is a theta series. The theta series, as we mentioned before, for Kolyvagin's problem, if we carefully choose phi 1, phi 2, then the Fourier coefficients of this theta lifting theta will give you this, and will give you an analytic shot of a given class X. So the inner product of this particular form has relation to derivative of air values. So we expect this kind of formula can be used to start the Kolyvagin's problem. Now let's make several remarks on this arithmetic Rallis. So first, previous work on Rallis inner product formula and arithmetic Rallis inner product formula were established by Ziegler formula or arithmetic Ziegler formula and the so-called doubling method. But our approach does not involve in doubling method. Instead of doubling method, together with arithmetic Ziegler, we set up a decomposition formula or vector periods. So this formula has long story. First, what Perget started this what vector period in his famous series of his famous work. But later on, Jaguet developed the technique of relative trace formula to develop what Perget's work into formula, not just property. So there are two kinds of vector periods formula. And one is related to base change of this pi. Another one related to quadratic twist of pi. And both of them can be proved by either Ziegler or relative trace formula. And the second ingredient in our work is the Grosssacker formula proved by Yuanzhang Zhang. So this theorem can be can be proved also holds for in general and over to the real field. And the certain form of this arithmetic Rallis inner product formula for the pair SO3 and SL2 was first conjectured by Kudla in certain explicit form. But in his conjecture, the right-hand side, this product of V is not like this, is some, they say some constant. And in certain case, over Q, for example, like square-free under square-free condition. So this ARI over Q was proved by Kudla, Rapport, and Yang, and also Yang, Tonghai Yang and his students, the sequence of their work. Now let's talk about this application of Kolyvagin as a problem. So given any quadratic twist family of elliptic curve over Q, suppose I give you any base A in the quadratic family and give you two classes equivalent class x1 and x2. So if the first one has sign -1, second one has sign +1, such that the x2 is the quadratic twist of x1 by some negative integer. Or negative, yeah, integer. And let pi a again, so a is the curve with sign -1 and so on. We mentioned before. So, and the V is the trace zero subspace of the incurrent quaternion algebra B. And for suitable test vector F and phi, as we mentioned before, so that the Fourier coefficients of theta lifting are exactly this analytic sharp. So, and for any D1 means A twisted by D1 belong to this X1. So for any D1, this we can define a certain twist of this F and phi. Then we consider this theta lifting associated to this FD1 and phi D1. So there is an integral structure given by Fourier coefficients. And this for this theta, somehow you can take this p to the some power times a primitive one. And this p to the power, this p to the power exactly basically is half of the order p order of the analytic SHA of A di. But this D1 is fixed. So only D2 varies. So basically this touches the problem for this minimal of p order of analytic SHA when A runs over in X2. So it follows from the arithmetic Rallis inner formula and a certain arithmetic vector series formula. So this arithmetic vector series formula is similar to what Jagay developed, the vector series formula, but the arithmetic situation. So this is follow from this two formula. Then we can make the difference between this analytic SHA in this x1, which has sign -1, and this minimum of analytic SHA when A runs over x2, which has sign +1. So here, and this difference is given from the formula given by 3 terms. So the first term, which I denoted here, I, involves local integrals with test vector, this local component of F and phi. And actually we can make this local integrals explicit as our previous work, with joint work with Li Chai and Jie Shu in what's called Jie formula, toric series formula. And then, but this explicit computation for I is very important for the Kolyvagin problem, because previously you don't know which kinds of prime were involved in I. But by this explicit computation, the computation of the local integrals, then we know which kinds of primes we just need to exclude, so that the difference of the two minimal analytic SHA were given by the remaining 2 terms. And the remaining 2 terms are in terms of the representation itself. And in this plus sign case, both of x1 and x2 are plus. So Prasanna started these 2 terms in his thesis. So using this Iwasawa main conjecture of Rubin, this will give some bound of these 2 terms. Okay, so I finished my talk here. Thank you very much. Hello?
Yeah, thank you very much. Yay. So we have 1 minute left and no time for questions, and I don't know how to handle these questions, but thank you very much for your talk, and let's all give Tian a big hand. Thank you, Tian. So that brings
Professor Shrita.
That brings this session to an end. Thank you.
Thanks.
Bye.